Hey folks, today's topic, we're talking about parent functions and transformations, so we should feel pretty good about our parent functions. Hopefully, you already did the assignment where we reviewed parent functions from last year and transformations. Just a quick review of some function verbiage, so just so you know some terminology when it comes to what a function is. So I'm not going to go through and read this. You should, okay? It's one of those situations where if I were you, I would read this whole thing, and then maybe come back and take a look at how we're breaking down the notes, and then I would just highlight some things that are really important. If you just look at what I'm talking about, you might be missing out on some of the finer details. So I'm just going to talk about kind of the highlights where I think if you're what you should do is go back and really actually read this and make sure you understand what we are talking about when we're talking about transformations and parent functions. Okay, so just a quick little review here. Functions, lots and lots of functions when it comes to the calculus. All right, so what is a function? So we have to do a quick review. So let's jump down to, I've got my highlighters here. So I've got 3 different highlighters because I'm going to highlight things a little bit differently. So the same color will be related to each other, if that makes sense. Okay, so the thing that differentiates a function from a relation. So a relation is any relationship in mathematics, okay? The specific type of relations that are called functions, hopefully you remember this, you've seen it at least algebra 1, algebra 2, and pre-calculus, is that for a function, every input can have no more than one output. In my class, we say it, for every x, there's exactly one y. So you don't have to have an output, but if it does, there's only one output. And there's something called the vertical line test that we could use that checks to see whether or not a relation is a function. Maybe you remember that from Algebra 2 and Pre-Calc. So the collection of all inputs, allowable inputs, is called the domain. So if we're talking about, let's say, the square root function, the allowable inputs do not include the negatives. So the allowable inputs or the domain would be the non-negatives, 0 inclusive off to infinity. The collection of all outputs generated from the inputs is called the range. So if you have, let's take the quadratic function. If you square any number, you're always going to get a 0 or a positive. So the range of, let's say, a quadratic would be 0 inclusive up until infinity. So just a quick review of what domain and range are. He goes through a little argument here on talking about why functions are important. I think this is a nice thing to remind you of. Functions cannot have repeated inputs. Look, you could have the same output every single time of a function. So it's legal. Let me highlight that first. So functions cannot have repeated inputs. It's legal, though, to have the same output. As long as it comes from a different input. So for instance, he uses the example of golf. So Tiger Woods has won the Masters 4 different times, but they happened on separate years. So if the input of my function is 1997, the output is Tiger Woods winning the PGA. In 2001, that's a different input, but the output, Tiger Woods wins the PGA. 2002, he wins the PGA. 2005, he wins the PGA. What you can't have is 1997 co-winners of the Masters. So in 1997, it was just Tiger. It couldn't be Tiger Woods and Phil Mickelson both won in 1997. Okay, so just an input can have lots of different inputs, can have the same output, but 2 different inputs cannot have the. Well, let me try that again. One input cannot have 2 different outputs. So functions are important. So we're going to kind of look at functions in 4 different ways. He calls this the rule of 4. I've never really heard that before, but I do know, according to College Board, that we're looking at functions in 4 different formats, and those 4 different formats are verbally, numerically, visually, and algebraically. And he's got a little chart on the next page, which I think is nicer. So I'm not going to get into this too much before we cover the rest of this page. So a couple things to point out. Here's our family of functions. You should know these by heart. You don't need to know exactly every detail, but you should have a pretty good idea. If I say, what does the absolute value graph look like? You should have a picture of that in your head. If I say sine and cosine, you should have a picture of that in your head. Cubic, cube root, all these are ones that are worth memorizing. So if you haven't memorized them yet, you need to get to that spot. And then that continues. We've got some more parent functions here. Step functions, I'll talk a little bit about those. This is the normal distribution curve, I think. I mean, I don't know. This one doesn't come up a whole heck of a lot. So some of these really weird ones. I mean, this is a semicircle. That's an important one. It's kind of weird. They cut off half the page from before. So these are the equations for those. I don't know why he didn't hit enter a couple times on this page, but I'm not complaining. All right, so let's take a look at one family of function in its 4 different forms. So we've got algebraically, f of x equals x squared. So algebraically means by the equation. Visually, that's the graph of this equation. Numerically, that's a data table of all the points, a sampling of points of this curve. There's no way we could make a table of all the points. We wouldn't have, there's infinitely many points. Our table would go forever. And then verbally, this is the one that I don't know. We don't use that one that much. Function is a set of all squares of the inputs. These 3 are the real biggies. You should be fluid, being able to go back and forth between all 3 of these things. So if I said, let's pick an easy one, absolute value family. If I wanted you to tell me what the equation for an absolute value function was, could you do that? Could you tell me what the graph looks like? Could you generate a table? Yeah, hopefully you could already do those things. And if not, we'll have a chance to review some of them. So, like I said, one of the most important skills for AP Calc is to be able to see the graph of a function by looking at its equation. So if you see an equation with the absolute value bars, you should know that's pretty much going to make a V. Now, these, he calls them, I don't know if this is a gag, he calls them mother functions. I call them parent functions. Mine's a little bit more PG. His is a little more risky. But these parent functions, what's interesting about an x squared function is you could do a lot of weird stuff to it, and it still is this basic shape. You can stretch it, you can shrink it, you can dilate it, you can translate it. But it all comes from this family, this basic parent function. So we're going to talk a little bit about what those transformations are. So here's his format. Now, a couple of these I'll talk about aren't as important. I would say this one is not as important. I don't see it as often, but we're going to talk about what role each one plays. All right, so this should be old news. You should already know, what does that do to our curve? If you put a number out in front, if I take the x squared graph and then I put a 3 out in front of it, what is that going to do to my x squared graph? Hopefully you know that it's going to cause it to make a vertical. Now, I use the phrase stretch or shrink. I should really say stretch or compress. So the number out front, now notice that's getting multiplied to the function. So that's going to affect the y values. It's going to affect the function values. That's why it causes a vertical change. You look at this here at the end, this is also connected to the function. It's not connected to the x. So this is also going to cause a vertical change. But I'm going to talk about, let's talk about those 2 right now. So this one and this one you should feel pretty comfortable with. This one and this one. What do we call those? Hopefully you already remember. We call those shifts. Now our fancy term, we called them shifts last year. I'll call them shifts in person, but we should probably call them translations. Now who's this connected to? It's with X, so it's going to be a horizontal translation. And then I'm going to write opposite in parentheses. Remember that that one does the opposite of what it says. This is not connected to X, therefore it must be connected to Y, and therefore it means it's going to do a vertical translation. And remember, this does the same as what it says. So if there's a +3 at the end, it'd move my picture up 3, my graph up 3. If it said -2, then it would move my graph down 2. This is the one that I don't do a lot of in pre-calculus. First of all, who's it connected to? It's connected to X. It's inside of the function. So it's not going to affect the Y values, it's going to affect the X values. So this is going to be a horizontal stretch or compress. But just like the horizontal, anything with X does the kind of the inverse of what you would guess it should. So if I have, let's say, a multiply by 2 here, this is going to multiply by 2. It actually compresses the graph horizontally by 2, you could think about it as multiplying by a half. It takes the graph and makes all the X's squeeze in. So it's just like this is the opposite of what you'd think it does. This does the opposite of what you'd think it does. And so I'm going to go back here and I'm going to write same underneath that, with the idea that if you have a 6 out in front of a function, it's going to stretch your graph by 6. If you have a 1/2 out in front of your function, it's going to compress your graph by 2. Where if it's in here with X, it's going to do the exact inverse of those. So you can kind of go through, this is math speak. When you take your first college math class, and if this is one of the topics, this is the kind of stuff you'll see. I'm not going to go through it. I mean, what we just talked about on the other side and doing some examples, I think, makes a lot more sense than all this. But this is math language. It says let's just take a quick look at, let's pick something randomly. Okay, if C is greater than 0, okay, C was the thing connected to X, so that means it's going to do a horizontal shift to the right or to the left. And remember, if C is greater than 0, it goes, wait a minute. Is he wrong? If you're positive, it goes to the right. No, I disagree with this. Huh. Right? Help me out. Let me know when you come back to class if you agree with me or if you... Yeah, I think he's got that backwards. I know he does, right? If C is greater than 0. Oh, he's already got the minus in there. I'm sorry. See, I think about the minus as being part of the C, so he's not incorrect. Anyway, all right, so when applying the transformations, you can't just willy-nilly do them in any order. Mr. Wojo and I actually had a conversation about this because I couldn't get one of my graphs right, and it's because I did the shifts before I did the dilations. So the multiplying, the compressions and stretches, those are called dilations. So you must apply dilations, reflections first. Shifts, translations, those will come last. So kind of like the order of operations, kind of makes sense, right? You do multiply and divide first, then you do add and subtract next. So to write a standard form of transformation, you can go through that if you want to read that there. So here's our first example. So this is our function. What I'd like you to do now is to pause and write what each piece of this looks like. Now, I guess I should point out one thing. They're kind of sneaky here. Notice what they did. They wrote it like this. You'll see that a lot in textbooks. when your leading coefficient is negative, you'll see that they'll bump the number at the end. They'll bump it up front so that this doesn't start with a negative. Why they do that, I don't know. I guess it's a little nicer, but that's where that comes from. So they just took they moved the 5. They moved the 5 from the back, which is where I think it belongs, and they moved it to the front. So like Corpy, his advice is, first thing you should do is move things into a form that looks like this so that you can apply your transformations. So what I'd like you to do right now is to pause the video. Well, after I talk, pause the video. Let's do one together. How about this? And then I'll show you exactly what I want. I want you to circle the part of the function and say what it's going to do. So for instance, if I take that negative out front, what is a negative going to do to my function? What's a negative going to do if you have, what's the graph of x squared going to look like if I put a negative out in front of it? It's going to reflect it, but which way is it going to reflect it? Well, is the negative getting attached to the function, or is the negative getting attached to the x? It's getting attached to the function, which means my function values will reflect. So this will be a vertical reflection. That negative will cause a vertical reflection. Does that make sense? Try to circle the 7 and say what you think the 7 is gonna do. Pause it and come back. Okay, let's see how you did. So I'm going to circle the 7. The 7 is going to cause, now you can't just say stretch or shrink. You have to say in which direction. Sorry, stretch or compress. This is a vertical stretch by 7. It's going to take those are my function values. It's attached to the function. So it's going to make all my y values, whatever they were before, they're going to be 7 times bigger. All right, let's pause here again. Circle the 2 and write a little note to yourself. Pause. Try this on your own. Go. Okay, so the 2 is connected to the x. It's not connected to the function. It's inside of the function. Those do the inverse of what you would think it would do. So this multiplies by 2. First of all, it's connected to x. So it's a horizontal. It's a multiply by 2, which is actually going to compress by 2. Or put it in parentheses, it's going to multiply by a half. So it's going to take my x values and squeeze them in. They're going to be half as wide as they were before. So the point that was at 8 will now be the point at 4. The point that was at 6 will now be the point at 3, and so on. All right, let's have you pause again. Circle the +3. Tell me what you think that causes. Go. All right, so this is attached to the x, which means it's going to do the opposite of what it says. It's an add, so that's a translation. So this is a horizontal shift, and it does the opposite by -3. Now maybe you wrote something like shift back -3. Sorry, shift back 3. That'd be fine. I'm not going to be that picky. I just want you to have an idea of how to move all this stuff around. Last one, circle the 5 and pause. Discuss it. Okay, hopefully you wrote something like vertical shift by +5, or just, you could say shift up by 5. That'd be fine too. Okay, so from here, and if you read, this is his language that he used. Pretty much the same as what we used. I said vertical shift. He said shift up. So a vertical shift of +5. I don't care which way you say it, as long as you've got the basic idea. So let's look then. What happened to our function here? First of all, what's the parent function? I guess I didn't say that right away. What family of functions are we talking about here? Hopefully you noticed it's the one thing that doesn't get circled. That's the natural log. So that's my family, is the natural log. Before you flip the page, make a little sketch of what natural log looks like down here. All right, let's see. Natural log looks like all the log functions. So exponential functions go like this. Whoosh, they launch up. Log functions do the same thing, but they go sideways. So they launch, instead of launching up like an exponential, the log function is asymptotic to the y and then launches forward. Anyway, so let's see, what did we do to our translations here? Or what did we do to our parent function? So here's our natural log graph. First thing they did was a reflection. So the negative out front caused the graph to reflect vertically. So now it looks like this. The -7, that's attached to the function. So it's going to take all the y values and multiply them by 7. So what was, let's say this is 2 negative, I can't even say what it is, -1, let's say. 2 is now -7. Notice they changed their scale. See how many more tick marks there are over here? So that stretched it vertically. Then we attach the 2 to the x. So that's going to be a compression horizontally by 2. So notice how far this was sticking out. Now it's half as wide as it was before. Notice this hit at the 1 on the x-axis. Now it's hitting at 1/2 because all those x values compressed down. Then we did a horizontal shift because it's attached to x. It did the opposite of what it said. So this was touching at 0.5. Now it's touching at -2.5 because 0.5 take away 3 is -2.5. And then finally, they took the graph and shifted it up 5 units. It's easiest to look at the y-intercept for that. Shifted it up 5 units. There you go. So those are all our translations. Actually, I'm going to write them underneath each one. This is a vertical reflection. This is a vertical stretch by 7. This is a horizontal, what's our word again? Horizontal compression. I'm just going to write compress by 2. And I always like to kind of put in parentheses 1/2 over here as a reminder to myself that really means you're multiplying by 1/2. It does the kind of the inverse or the opposite, quote unquote, of what you're thinking of. So +3 next to x is going to be horizontal, and plus does the opposite. So this is a horizontal shift. -3, maybe you write back 3. Either one of those are fine. Then this would be, the +5 would be a vertical shift +5. So I'm going to go back and circle these in each color, what that piece did individually. So I think this is kind of cool. It's kind of interesting that it doesn't matter what family of functions you're working with. They're all going to do the same shift. So if I did, let's say I took a function, let's say I wanted to look at f of x equals -7 sine of 2 times the quantity x plus 3 plus 5. That would take the sine curve and just do all those switches to it. Let's say I wanted to take the function f of x equals, this will be harder. Let's see if I can do this with a squared. So it'd be -7 quantity of 2 times x plus 3 squared plus 5. So there's my transformations. The exact same transformations would happen, but to the parent function of x squared versus sine versus natural log. All right, so this was his sketch. Look at, is this sketch the exact same as this sketch? No, that's not our goal. He didn't even label the y-axis. But the idea is we're just trying to get a sense of what that curve looks like. Absolute values are super easy to, they make total sense. Like maybe to me, maybe I shouldn't say that. But they seem to make total sense. If you take, what are these again? F of x are your function values, y values. And what's weird is you bounce back and forth between those terms, so be comfortable with either way. So f of x are your function values, are your y values. Therefore, Remember this from your geometry days. Those 3 dots as in a triangle mean therefore. Therefore, absolute f of x is going to do what to all of your y values? Absolute f of x means all y values are positive. I should be a little picky. Remember, if it's 0, the absolute value of 0 is 0, which is technically not positive. But anyway, so what's cool about it is it just takes your function. So here's the graph of, here's our log function, natural log function again. But this time we took the natural log function and made it absolute value. You literally just take all the y values and make them positive. So these y values are already positive, so those stayed the same. Positive stayed positive, but all the y values that were negative, which are all of these down here, those are going to flip up and become positives. So if you absolute value a function, draw the parent function, and anything that's below the x-axis, anything that has a negative y value, is going to flip up to the top. And then our last transformation. What if the absolute value goes around the x value? So now these are my, let's do a color we haven't done yet, maybe a purple. Purple won't show up very well. How about a nice puke green? So these are my x values. Let me do it like I did on the other one. What did I do? I did it. X are called the x values. Therefore, absolute x mean all negative x values act like positive x values. Here's our natural log function. The transformation this time is we're taking the absolute value of my x's. So right now, if you just did natural log of x, let me kind of write that over in the corner here. Natural log of x. If you put a negative in here, it blows up. The natural log of a negative is undefined. Natural log of -4, non-real answer. Natural log of 0, non-real answer. Natural log of 1, you're good to go. Natural log of 52, you're good to go, okay? So natural logs can only be of positives, but if we absolute value all of our x values, that means when we plug in natural log of -4, well, when I put absolute values around that -4, it's going to make that into a +4. So the natural log of alpha f1 absolute -4 is going to be the exact same thing as the natural log of 4. So my point is, once you have the absolute value around your x values, the negative numbers will look exactly like the positive numbers. So these positive x values get flipped into these negative x values. So the negative x values behave like the positive x values. So basically what happens, whatever his note here, where do I want to, maybe I'll use the green. Where's the green? Okay, so he says leave quadrants 1 and 4 and then reflect. I don't think I wish, yeah, we can leave it. Leave quadrants 1 and 4, disregard anything in 2 and 3, and then reflect across the 1 and 4 across. So basically he's saying whatever was here, get rid of it and take whatever's in these two and reflect it over, because negative x's on their own don't exist anymore, because as soon as you put in a negative x into this, it becomes a positive, and then you'll never have any negative x values. I thought this was kind of interesting just to kind of highlight what would happen if we put an absolute value around our function and around our x values. So what would this cause? This would cause all y values to become what? All y values are positive. I just dotted my v for some reason. I don't know why. All y values would be positive, and all negative x would equal positive x. So whatever's happened on the positive x side would get flipped over into the negative x side. Now, you might say, well, why don't I just do all that? You did this on your calculator. Why can't I do it on my calc? A lot of this stuff will not be in the calculator sections. Most of this class is non-calculator. There's a couple of times where you'll need your calculator, and you do have to be fluent with it. But for the most part, you're going to have to do stuff without calcs. Yeah, so this is worth talking about. I don't know if you have to master this today, but it's worth talking about when you're looking at a function. So what family does this sort of feel like? Hopefully you said it felt like the reciprocal family. The problem is it's not quite that setup. It's not quite this because there's an x on the top and the x on the bottom. So one of the tricks, one of the things that we're going to learn and use multiple times is to take a rational function and actually divide it out and see what the resulting quotient looks like. So if I take x minus 1 and divide it by x, I can't do this synthetically because that would have to be a 0 up there, and that would not work very well. So what we're going to do is we're going to do this. This is his work for it. I would have shown it like this. I'm taking x minus 1, and I'm dividing it by x. Remember how this works? I would say x goes into x one time. Then I take this 1 and I multiply it by the x. Then what was the saying? Draw the line, switch the signs. X minus x is 0, and then the negative 1 drops down. Now I can't put an x into a negative 1, so the best I have is 1 plus, and then remember we take the remainder and we put it over the divisor. So it turns out that this function is part of the reciprocal parent function family. It just didn't look like it to begin with. Notice what they did then. He took this and algebraically moved some stuff around so that it really looked like the reciprocal family. So he put the negative 1 over x first plus 1. So what's this negative? What family are we? Reciprocal. What's this negative going to do to all your y values? Vertical flip. What's this plus 1 going to do to your picture? It's going to shift it up 1. So we still have, remember, the reciprocal family is normally the x and y axes are the asymptotes. That was shifted up 1. And then we also took all of our y values, they're usually in these two quadrants, and reflected them over. Okay, so that's hopefully kind of a crash course reminder on how to do some of our transformations and kind of remembering some of the parent functions and getting a chance to talk about some of those. I'm going to also do a video on the homework for this. I'm not going to do this going forward very often, but I think this one is worthwhile to do a video on because it's pretty intense, some of the stuff that we talk about. All right, good luck. If you want to try the homework first, go for it. Y'all, definitely you should try to do it first. Never mind. Yeah, try to do it first and then only use the video as a reference if you need it. Good luck.